Welcome to our first lesson, which is chapter 1 from the book, and it is Introduction to Statics Mechanics. What I want to do today is go through some of the objectives for this chapter, which is to define mechanics, give you some examples of the application of static mechanics, tell you the fundamental principles that we are going to be applying throughout this course. Make sure to convey to you what units we want to work in and how we use significant digits, and the type of problem solving strategy we are going to apply. Once you go through this course and this particular lesson, work on the example problems, you will be able to work in SI and US units and apply the smart problem solving strategy. So let's begin with the question of what is mechanics. So mechanics is the study of bodies under the action of forces, and as you will see, it is the foundation of many engineering topics and is therefore an extremely important and indispensable prerequisite to several engineering subjects. There are two broad categories of mechanics. The first one is called rigid body mechanics, and what a rigid body is that it is basically a body which is a solid, right? Of course, it may be a solid connected to other solids through chains and links and things like that, but overall it's a solid body. Now within a rigid body, you can have statics mechanics and dynamics mechanics. Okay? So what statics and dynamics are is that statics basically refers to the mechanics when bodies are in equilibrium. For example, they are either at rest or moving at a constant velocity. And that's what our course is going to be about. Dynamics, on the other hand, is the mechanics of bodies that are undergoing accelerated motion, which is the topic of another engineering class, which is Engineering 240. The other type of mechanics is deformable body mechanics, and this has to do with the motion of fluids. For example, it could be a gas or it could be a liquid. Now, since many of you, or probably all of you, have taken a basic class in physics, you may already have encountered some of the fundamental underlyings of mechanics. And in fact, mechanics is very closely related to physics. So that's why one of the prerequisites is, of course, physics. And as you will see, statics builds on many of the concepts that you've already learned in physics. So let me give you some applications of static mechanics. Now look at these two images here, and in the image right here on the left, what you see is this person is trying to adjust the position of the car as it's being loaded on the ship. What you see here is this little girl hanging off of a tree. And the question that we are going to be able to answer using static mechanics is that, what is the tension in the cable supporting the person, like this kid, or in the rope that is being used to align the car. And this is the kind of problem that we will be able to find an answer to using our principles of static mechanics. Here's another type of problem that we will be able to solve. There are many examples in engineering analysis where loads are being applied over large areas, and these are called distributed loads. And then very often it is convenient to be able to take that distributed load but represent it as a concentrated force. And this can be done by finding what is known as a centroid or the center of gravity of the load. And that's something else that we will be able to do by the end of this semester. Here's the third type of problem we'll be able to solve, and that is about equilibrium and the kind of forces that members are facing when they are, for example, part of a bridge, part of a frame in a body like this, like a bicycle, or parts of a machine. And these load-bearing structures need to be designed based on what they are going to do in the real world. And so as an engineer, it is important for us to be able to calculate the forces and loads that these objects are going to face, so that we can choose the materials correctly and design them correctly. Understanding static mechanics also leads to discoveries, for example, improvements in machines, And even this very interesting example here, some of you may have heard of Dick Fosbury, who actually graduated and became a very well-known civil engineer. But in 1968, he was just about to start his college career, and he took part in the Olympic Games in Mexico, and he won the gold medal there in the high jump by using this unusual technique of high jumping at that point, which is going over the beam with your back by launching yourself in a backwards direction. And so this technique is now called the Dick Fosbury technique, or the Fosbury flop. And what he discovered is that this technique allows you for the same amount of force that can be generated by two people, this one allows you to go higher because the actual center of gravity of your body is lower than your actual body position. And so the center of gravity passes below the bar here, while your body actually goes over the bar, and this can be done with lower forces than required to actually jump over the bar if your center of gravity is going over the bar. And so this technique is now widely used by every high jumper and also by pole vaulters, and it's based on the science underlying the calculation of the center of gravity. Okay, so now let's turn to some of the fundamental ideas we're going to use, some which you already have encountered and some new ones that you will see partly in this class, and then if you take dynamics. So there are 6 fundamental principles that are used in mechanics. And the first one comes from the addition of vectors, is known as the parallelogram law of vector addition. And since forces are vectors, and since our whole class here is focused on dealing with forces, the law of vector addition of forces will be a very important part of problem solving. The second one is the principle of transmissibility, and this has to do with how you can take forces and change the position where they are applied to, as long as you don't change the magnitude and the direction and the line along which they are acting. Okay. And the third one is Newton's first law. Of course, we have 3 laws of motion. We will be using the first law in this class quite extensively, and that's because we're going to be dealing with systems in equilibrium, which means that the resultant force on the system is 0. The second law is something that we will use in a later class. It will not be used as much in this class here, and neither will we use the third law or the Newton's law of gravitation. But these 6 laws together are the fundamental principles of mechanics, both static mechanics and dynamics. Now let's discuss briefly about the units we want to use in this class. Of course, what you will see is that when you're assigned a homework problem or a test problem, it might be in the metric units, the SI units, or it might be in the US system of units. So you need to be comfortable working in both units. Now, it turns out that the fundamental units are basically just 3: mass, length, and time. And everything else can be derived with respect to a combination of mass, length, and time. In the case of dynamics, we also include force as a fundamental unit. Okay? And together we have 3 basic units, which are mass, length, and time, and 1 derived unit called the force. In the SI system of units, mass, length, and time are given by meter, second, and kilogram. That's shown here. And our derived unit, the force, which is a product of mass times acceleration, is given by the newtons, and in the basic units it's kg meter per second square. In the case of the US units, though, the basic units are the length in feet, time in seconds, and force in pounds, and often this is also called as pound force. So you can see the difference here between SI and US is that the basic units differ in the fact that the SI uses mass while US uses force. So in the US units, the derived unit is the mass, and it is force over acceleration, and it's given by pound per feet per second square, and this is also commonly known as 1 slug. Okay. Now for you, you need to be just familiar in terms of converting from one unit to another. because you will see that in problems you might have a mixture of the two units, or it might specify you to find a solution in the SI units, although many of the parameters are given in the US units. And so you just need to be comfortable changing from one unit to another using these kind of conversions here. Now the other note I would like to mention is about how many significant digits to use when you present your numerical solutions. And to answer this question, we need to think about what the accuracy of a solution depends on. So it depends on two things. One is your accuracy will obviously depend on the accuracy of the data that is provided to you, right? So if you are given something in units of tens of meters, it may not be possible to find a solution that is with a resolution of a millimeter or a centimeter. So you have to think about the accuracy of the given data, and then the accuracy of the computations that you perform. Okay, so remember that your solution cannot be more accurate than the less accurate of these two aspects here, the data or the computations. Okay. Now in terms of significant digits, it's very tempting to put down whatever the computer or the calculator spits out, but the calculator and the computer are not limiting the number of significant digits because it doesn't understand accuracy, right? It's you who has to account for the accuracy of the data and the computations, and remember to put down the right number of significant digits. So for those of you who want a reminder about significant digits, you can click on this link here and it will give you a one-page summary of how to think about significant digits. But for the purposes of our class here, it's important to remember that as a general rule, in engineering problems, you generally don't know things to greater than 0.2% accuracy. And what we're going to do is we're going to say that if we have numbers that begin with 1, then we can go up to 4 digits in significant digit number, while if it is not beginning with 1, we can stick with 3 digits. So for example, 40.2 is 3 digits, while this one begins with a 1, 15.58, so we use 4 digits. Okay. So this is a rule you can follow, and as you go along, you'll become more comfortable with it. Finally, let me just review the problem solving strategy we're going to apply throughout this class. And initially, when I solve example problems, I will use this, and then later on it's up to you to keep using this approach as you solve problems when you're practicing at home. Okay. So this technique is known as SMART, and SMART stands for S for strategy, M for modeling, A for analysis, and R for reflect, and think, which gives the T. So it's SMART. And as you will see, it's basically a systematic stepwise process to understand what's required in your problem, create a strategy based on what's required. So that means, you in your strategy step, you are trying to determine what physical laws and principles you need to apply to solve the problem. Modeling, which allows you to basically picture the solution by drawing a figure, finding out what is unknown and what is known. And then once you have that, you start your analysis, which is where you write down your equations, you manipulate algebra, you do the numerical calculations and things like that. And finally, when you found an answer, you take some time to reassess or reflect, go back and make sure you're doing things properly, and most importantly, to think about whether the answer is reasonable physically or not. Okay. This is also a time where you want to maybe try a second approach to solve your problem to see if you get the same answer. Okay, so with that, I'm going to wrap up this this introduction to the class, Engineering 230, which is statics. Please make sure to read through all sections of Chapter 1 and any supporting material that might be available with this lecture. And I look forward to joining you for the next lesson, which will be up shortly. Thank you.